Okay. Welcome, everybody, all four of you. I'm not too fond of course outlines of things, but this is the two topics that we're going to be focusing on. One is quantum walks, and the other is quantum homomorphisms and quantum automorphisms. Now, and basically the plan is to do the quantum walks and then the quantum homomorphisms. Now, to make any progress on that, we need some tools, and the tools are coming from algebraic graph theory. And so there's the little list there. There's a little list of the things we'll be covering in terms of algebraic graph theory. The only one that's a bit unusual there is walk generating functions, but I'll be trying to cover that in more detail. So going back again, so we're going to talk about quantum walks and quantum homomorphisms, but to do that I need to develop a number of tools. And so today I'm starting off on the tools in a slightly funny fashion. So, and now most of what I'm saying in terms of linear algebra will be in my notes on linear algebra that I've given a link to on the website. Now, I should say, if you go to the field website, which I think you will have, there's now a link to my webpage. And on that webpage, I've got links to various notes and some previous lectures and things. And so the information about linear algebra will by and large be in those notes. Okay, so I need to talk a bit about norms. Now, the problem is that we want to work with the matrix exponential. Okay, and sometimes I find this a bit of a shock for the students because they haven't seen anything like a matrix exponential before, so I want to go through the details. The other thing is that, well, the matrix exponential is what you use to define a continuous quantum walk, so we need for that. But the matrix exponentials turn up in lots of places in quantum mechanics. Okay, so it's a basic tool. Now, in their situation, life is more difficult because this matrix A, well, it's an operator, and it's probably an operator on interdimensional space, and it may not be continuous on the entire space. So there's all sorts of difficulties, but we're just looking at square n by n matrices now over some field, so say a field of characteristics 0, really. Now, the problem in this case is to show that the limit on here, that this is well defined. Okay, so what I'm trying to do then is to explain that, that in a certain sense that this definition makes sense. Now, so to do that, when you want to prove that x for little a, where a is your number, is well defined, you use absolute values and fill around. I'll come back to that. So we can't define the absolute value of a matrix, but we do have norms for matrices. And that's what I want to talk about briefly. So the first thing here is just a definition of a norm, and this is absolutely standard. And so I'm assuming that you've seen that. If I'm wrong, you should be letting me know. So we have a norm, so it's non-negative. It takes value 0 if and only if the argument is 0. And the absolute value of a constant times x is the norm of a constant times x is the absolute value of constant times the norm of x. And we have the triangle equality. So they're the three properties that we require. And so lots of examples. The one used to using is the Euclidean norm. Okay, the sum of the squares, the absolute values, that works for real or complex. There are also what they call the little LP norms. So you're taking the pth powers, the absolute values, and then you take the pth root of the entire sum. Now, I've never actually seen anybody use any value of p other than 1, 2, and infinity. That must be used somewhere. I haven't tried very hard. And then certainly the only value of p we're concerned about is 1, 2, and infinity. And let me make those concrete. A sequence is summable if its L1 norm is finite. The sum of the absolute values exists. It's bounded if the L-finity norm is finite. So this is the definition. The L-finity norm is the maximum value of the absolute value of an entry. The L1 norm is the sum of the absolute values. And the L2 norm is, as I said here, is just the Euclidean norm. So they're the three norms that might come up. Well, generally, we'll need more than one norm before we go on. Now, a norm vector space is complete if every Cauchy sequence of elements of V converges to an element of V. And a Banach space is just another name for a complete norm vector space. Okay. And you've probably never worked in a norm space which wasn't complete, so I don't know we need to worry too much about that. The standard example, we're generally working with complex vectors of length n, and that is a norm space and it is complete. We'll see others as we go. The other comment is we can get norms from inner products. So if you have an inner product in a vector space, then the square root of u comma u is a norm. And that's a very convenient norm. When the case if v is real, we recover from this, you just get the Euclidean norm again. If v is complex and the inner product is as I show here, the inner product is as I show here, then we get the usual norm on complex vectors. The comment I need to make here is that all physicists and many mathematicians put the complex conjugate on the first term here, and a number of math texts on the other hand will put the complex conjugate on the second term. Now, it doesn't matter too much provided you don't move the complex conjugate backwards and forwards in the course of operation, but this is the version that I'm using, and your lives might be a little simpler if you stick to it. So the advantage of this is that the inner product of u and v is u starred v. U starred is the conjugate transpose, so that's one advantage. And as I said, the physicists use this version. Now, I don't always follow the physicists. I won't be using bra and cat notation, for example, but I do follow them in this, so it seems more natural. So, okay, that's some general remarks about norms. Now, we want norms on matrices. And the one we're going to use is the, you just take the trace of A starred B. Now, if you think about that for a bit, what you're doing is you take the, well, I can define it in terms of this. The Schur product of two matrices is the entry-wise product. So you take the entry-wise product of A bar and B and sum the entries. So in fact, this is a version of the Euclidean norm. Okay, so there's no reason for taking anything else. And so this is a norm, and if you care, you can go and verify that. And this is the norm we're using. The only problem is what to call it. Now, it can be called the Frobenius norm, or the Hilbert-Schmidt norm, or the matrix norm, which is a bit ambiguous because there's lots of norms for matrices, or it could be called the trace norm, and I tend to do that sometimes too. The problem is that the trace norm is wrong because trace norm has got another meaning. Okay, so, but anyway, so the important thing is that if I'm talking about norms of matrices, where you see an inner product of matrices, this is what I mean. Okay, and so generally speaking, we'll work with that. Notice that the norm of the identity matrix would be square root of n. I'll come back to that in a bit. One way, the standard way of constructing norms for matrices from norms for vector spaces, and more precisely, if you have a vector space and you have an operator on it, and you have a norm on the vector space, then you can define norms on the operators. And this is very, very useful and generally standard. Now, this procedure, so we take a norm on the vector space and use that to define a norm on the operators. It gives me what I would call an induced norm, or sometimes called an operator norm. And it's simple enough. If we have an operator taking v to v, and we basically define the norm of L to be the maximum value of the norm of LV, where v ranges over the unit vectors. Now, if you're looking at exponential things, then there can be problems here, but in 5 dimensions, this maximum exists, okay? So we have no particular problems. And so this is what we call an induced norm. And the advantage of induced norms, well, it's written down later on, but I'll come to it now, is that the norm of a product, the norm of A times B, is bounded by the norm of A times the norm of B. And this is very useful. And so when you're trying to prove the exponential exists, you'd probably assume your norm has this property and use that. Now, the point is in 5 dimensions, as you've already seen, there are lots of norms, but they're all equivalent in some sense. So if you have a sequence which converges in one norm, it converges in the other. And so you could be sloppy about which norm you're using. And so it doesn't matter too much. But notice that what I was calling the Frobenius norm, the norm of the identity, as I said, is square root n. Okay, but if you're looking at an induced norm, the norm of I times A is equal to the norm of A, and it's equal to the norm of I times the norm of A. So the norm of I would be the identity for an induced norm. So the norm we use most often is actually not an induced norm. Now, this doesn't matter for two reasons. One is that all norms in 5 dimensions are equivalent. And secondly, you can fudge the, if you have a norm which is not induced, you can rescale it and convert it to an induced norm, but we won't be needing to do that. So are there any questions at this point? It's brave enough. Yeah, and so I'm mainly concerned with maps from V to V, but you can generalize this definition to maps from one space V to one space W. And if you have an induced norm and algebra operators, then the norm of AB is less than or equal to the norm of A times the norm of B. So in 5 dimensions, you're always free to assume that this property holds. Okay. This is repeating what I said. As I said, if the dimensions of V is finite, all norms are equivalent. If it's infinite, the choice of norms matters. It matters a great deal. And to give some idea of this, if you consider the vector space of real polynomials, there are a number of different norms you can define on this. Let me just do one. Do a few. So the idea is to pick a function, choose function. Yes, non-negative. And define the norm of PQ, the interval of PT, QT, FT, QT. Now that's the inner product. And so it gives you a norm, but you have lots of choices for this guy. And so there are lots of norms available to you, but here you're working with infinitesimal space. And so, but you know, it's a useful definite space. Now, the other issue is if you, a nice operator on polynomials is differentiation. It's a linear map, takes polynomials to polynomials, but it doesn't have a norm because the derivative, there's no bound on the, there's no fixed upper bound on the norm of the derivative of a polynomial, depending which norm you choose. There isn't a bound, so things break down fairly quickly. So if things don't work for polynomials, you don't have much hope of working with the general infinite case without paying attention to details. Okay, so now we get back to the exponential. Now, normally when I'm teaching this stuff and I want to talk about exponential matrices, I just say it exists and the proof is the same as the proof for real or complex variables. I'm going to give a slightly expanded version of that argument today. So suppose you dug out a textbook and you have a proof that x of a is defined for all complex A. Now, in that proof, if you replace the absolute value symbols by norm symbols for some induced norm and little a by the square matrix A, then that proof will immediately give you that the exponential of a matrix A is well defined. Now, most of the time, I think in practically all the time we use exponential matrix, that matrix is going to be normal, diagonalizable. And so in that case, there's another proof that the exponential exists, and I'll come back to that. So that's one reason why I'm not too worried about being sloppy here. So I'm saying you take your proofs that x of little a exists, and that proof works for the norms. Okay, so by using norms in place of absolute values, everything goes nicely. Okay, so I mentioned norm matrices, and so I want to get into that. Now, the general principle here is in linear algebra, it's not very often that you find yourself working with just a single matrix. So for example, when you prove that a symmetric matrix is diagonalizable, it follows immediately that any polynomial in that matrix is diagonalizable. And the set of polynomials in a matrix is an algebra. It's a vector space of matrices that's closed under multiplication and contains identity. So a large part of the results that you're proving in the algebra can carry through, and they apply to algebras, not just single matrices. And so I'm going to talk a bit about that. So an algebra is a vector space for us with an associative multiplication and a multiplicative identity. Now, the analysts don't always insist on having a multiplicative identity for reasons which are good for them. But I will always be assuming that algebra has an identity. And so a subalgebra will contain an identity, and a homomorphism between subalgebras will map the identity of one to the identity of the other. Now, the comment at the bottom here is important, that an algebra is a special type of ring. So all the things you know about or you've forgotten about homomorphisms of rings apply to algebras. The algebra is special because it contains a copy of a field sitting inside it in the center of the ring, and so the ring is a vector space over some field. So in other words, you could say an algebra is a ring which is also a vector space. Again, the definitions don't matter too much, but real or complex polynomials form an infinite dimensional algebra. And the n by n matrices over a field form an algebra, and that's basically the one that we're using most. So that the matrices form an algebra. And as I didn't write here, but one example would be take the real polynomials in T. They would form an algebra. Okay, that would again be infinite dimensional. So that's just making this. I'm just making this explicit. Now, basically what we want to do is to diagonalize things, because it enables us to reduce our linear algebra problems to simpler subproblems. Okay, so you want to diagonalize things. Now, I've said if you can diagonalize a symmetric matrix, you can diagonalize any matrix in the algebra. I want to diagonalize, in some sense, diagonalize a larger class of matrices. And so the problem is, of course, that not every matrix can be diagonalized. And here's your standard example. So you've got to impose some condition. And I'm not going to come up with the weakest possible condition, but the condition I'm going to use is that an algebra of matrices is star closed if it contains the conjugate transpose of each of its elements. So the algebra of invariant complex matrix is star closed. Okay. The algebra of real matrices will be star closed if and only if it's closed and contains the transpose of each element. Okay. And so this is the property we need to get things which we can diagonalize. Okay. As I said, it's not quite the most general thing, but this will do for what we need, since our algebras are always going to be nearly always over the real or complex numbers. If you look in algebras over other fields, you may want to use a somewhat different definition. Well, you need to use a different concept. This is not too important. An element of a ring is nilpotent if some power of it's equal to 0. And an ideal is nilpotent if there's an integer k such that the product of any k terms in the ideal is 0. Now, if you want to deal with rings more general and the complex numbers, then you have to replace star closed by a condition on nilpotent ideals, but we won't be doing that, so you can relax. The simplest example, or convenient example, is the upper triangular matrices form an algebra. The subalgebra of the matrix algebra contains the identity, it's closed on multiplication. Okay, and so it's a vector space, so it's an algebra. Now, the strictly upper triangular matrices, if you have a matrix which is upper triangular and 0 on the diagonal, then some power of it is equal to 0, and so it's nilpotent. Okay, and so the strictly upper triangular matrices in that case form a nilpotent ideal. Now, in general, you can't diagonalize upper triangular matrices. Okay, I mean, there's no. If I thought I'd get an answer, I'd ask you, there is one class where you could do it, but in general, if you could pick up an upper triangular matrix, it cannot be diagonalized. Okay, and so if you're trying to diagonalize some class of matrices, it's best if it doesn't contain any triangular matrices. So the class of matrices we're going to work with are normal matrices. And a matrix is normal if it commutes with its conjugate transpose, or if it's real, it commutes with the transpose. Okay. Now, so this is the definition of normal matrix, and this is sort of the biggest class of matrices you want to work with, and I don't think we need to go beyond it in this course. So examples of normal matrices obviously include emission matrices, which A is equal to A star, and real symmetric matrices where A is equal to A transpose. Another important class of examples are the unitary matrices. U star is equal to identity, or orthogonal matrices. U transpose, U is real, and U transpose is equal to identity. And so essentially, the linear algebra you've seen takes care of case A. Okay, so doing emission matrices or real symmetric matrices, you've done that. So you just didn't express in terms of algebras. The extra case we need are unitary matrices and orthogonal matrices, and so they're normal, and we'll be working with them, and so we want to be able to diagonalize them. And the last comment there is fairly trivial. If a matrix is normal, any complex polynomial in that matrix is normal. And to get another class, if L is a unitary matrix and D is diagonal, then L inverse is normal. Okay, and so equivalently, if the matrix is unitarily diagonalizable, it is normal. And in a sense, what we want to do is to prove the converse. So the normal matrices are the matrices that we can diagonalize. Okay, they're also the matrices where the eigenvalues in some sense give you useful information about the behavior of the matrix. If your matrix is not normal, the eigenvalues are much less useful. So normal matrices are an important class. And the final thing in terms of the algebras is if you have a normal matrix, then the algebra generated by n and n starred is star closed and commutative. Okay, now the angle brackets here are not the inner product. This is saying this is the smallest algebra which contains n and n starred, so it contains all linear combinations of products of n and n starred. And so that's what this means. And clearly it's star closed, and it's commutative because we're assuming n is normal. So the point is, to work with normal matrices, it's actually more convenient to work with the algebra rather than the individual matrix. Okay, so you can do it without it, but it's easier to do it with it. And I remind you again, most of this linear algebra I'm talking about is covered in the notes I have linked to on my webpage. There's another definition which I've set up as an exercise. Simply a complex matrix is normal if and only if for all vectors u, product of mu with itself is equal to the product of m star u with itself. Now, I'm not quite sure what you do with this, but this is a characterization and it's a nice exercise, and it's on the list. And so I want to diagonalize things. Okay, and so diagonalization actually means you want to find, well, if you think about the real symmetric case, your real goal is to find an orthogonal basis of vectors, each of which is an eigenvector for your matrix. So if I have a matrix A, to diagonalize it, we want to find an orthogonal basis of eigenvectors. Now, how do you do that? Of course, well, there's two things going on. So the first thing is you're going to assume, well, the idea simply is you take your matrix A and then you quote the so-called fundamental theorem of algebra to say, well, we know that there's an eigenvector. So there's a vector Z that AZ is equal to Z. Now, the thing then you notice is that if a symmetric matrix fixes the subspace spanned by Z, it fixes the orthogonal complement. Now, the reason it does this is because it's symmetric. This is why it matters whether a matrix is symmetric or not. If you think about it, why do we spend all this time fussing with symmetric matrices that are symmetric about the leading diagonal and not consider matrices that are symmetric about the back diagonal? In terms of sort of symmetry, they're both they seem the same. But the point of a symmetric matrix is key thing for a symmetric matrix is that for all x and y. So this is the reason why being symmetric matters. And one consequence of this is that if A fixes a subspace U, then A fixes U perp. Okay, so now we found our eigenvector. We have a one-dimensional space spanned by it. That gets fixed. We call that U. Now A fixes U perp. So now you've got a matrix, an operator acting on a space of dimension n-1. And by induction, you can, and it's still symmetric, or there's a line of proof required on that space. And so then you are, and so then you wave your hand and say, by induction, this n-1 dimensional subspace has an orthogonal basis of eigenvectors. Then you add the first eigenvector to, and there they are. So the point is that you can give a fairly concise description of the proof that matrices are diagonalizable. Okay, and the key things are the this symmetric matrix fixes a subspace. It fixes the complement, and secondly, and this is one point. This is one of the first points in the algebra where you really should be working with linear operators rather than matrices, because you've got a matrix acting on the big vector space, and now it's fixing U perp. Now, it's not a matrix on U perp because A is n by n, and U perp is n-1 dimensional. So what you have is a linear mapping, but it's still symmetric. And so the theorem you want to prove is that a symmetric linear mapping has an orthogonal basis of eigenvectors. And it follows from the existence of eigenvectors from this fact and induction. Now, are there any questions about this at this point? So I'm going to sketch a proof now for this more general result.
Chris, we need permission. We're working with a complex, right? So we need permission matrices instead of symmetric matrices.
Yeah, in this case here, I'm referring to the proofs that you'd likely have seen in your linear algebra course. Okay, and so they generally do real symmetric matrices in my experience. Now, what I'm about to do is to give a proof that works for normal matrices, and that will imply that a proof for emission matrices. For emission matrices, I'll say something about that as I go. But the point is, what I was discussing here is what you're likely to see in your undergraduate course in linear algebra, okay, where you diagonalize real symmetric matrices. They often don't go to the complex case. Does that make sense? So the proof for so I'm now looking at this algebra, commutative algebra matrices, which is complex matrices is closed under complex conjugation. Okay, and the proof that I can find an orthogonal basis of eigenvectors for this is the same as the one I just described for the real case. So the first comment is if the algebra fixes a subspace U of C to the n, then it fixes U to perp. Now, you've got to be a little careful. If a matrix A fixes U, then A starred fixes U perp. That's a little bit too simple to make an exercise, but if a matrix A fixes a subspace U, its conjugate transpose fixes U perp. But this is not just a matrix, this is an algebra. And so if it contains matrix A, it contains A perp. And so if A fixes subspace U and A is in purely A there, then A fixes U and A perp's also, A star is also in there, so A star fixes U. So in this case, we get if A fixes subspace U of C to the end, it fixes U perp. Okay, so we've got a decomposition U plus U perp, and A is fixing both. The algebra is leaving both parts fixed. And so at this point, as I said, this is a sketch of proof. You can show that if A has an eigenvector Z and B commutes with A, then B maps Z to an eigenvector of A. And so you can, once you have this smaller subspace, you can say, well, there are eigenvectors, and by induction, there's an orthogonal basis of eigenvectors. Now, the issue here is related to the thing I said before about the linear mappings. So the point is that in the sense, you don't want to write the proof in terms of matrices, you want to write in terms of linear operators. And so what we're saying, if A fixes U, that's an algebra of operators acting on U. Now we can get something more familiar. We take what we call restriction of element L of script A to U. Now the problem with restriction is normally when you talk about restriction, the usual meaning is you've restricted the domain. So you have a function on a set, you restrict it to acting on a subset. Now, what we're doing here is not exactly restriction. We're doing that. We're taking a subset of the domain and looking action on that, but we're also changing the codomain, because now it's mapping this subspace U to itself and not mapping the whole vector space to itself. And it's not mapping U into the vector space, it's mapping U to itself. So you've changed the codomain. Now, to define a function, you have to define the domain, you have to define the codomain, and you have to define the rule. Okay, now the rule in this case is obvious. We know how L acts, but my point is we've got this. So from our n minus 1 by n matrix, we get a linear operator on a space dimension n minus 1. Now we could, if we choose to, represent that by a matrix of order n minus 1 by n minus 1, but we don't need to. Okay, and so the issue then is we have a, okay, with having done that, we can then say, well, not only do we split the vector space into U and U perp, we can now say, we can now look at the vectors, look at these algebra consisting of the restrictions of L in script A to U. Now that is a commutative algebra and it's still Schur closed. And so therefore by induction, it's got an orthogonal basis of eigenvectors, and we can put it all together. And the last line here is filling out what I said about the existence of the eigenvector. So that if Lz is equal to lambda z, then the kernel of L minus lambda I is A invariant. But my point here is that first, it's a standard fact the normal matrix is diagonalizable. Okay. Second, that the usual proof with attention to details still works. Well, it's not, actually, it may not be the usual proof. That the proof that I sketched for the real symmetric matrices holds in this case. You just have to think a bit more carefully what the bits are. And so the conclusion now is that, in particular, any normal matrix can be diagonalized. And so it includes all emission matrices, and it also includes unitary matrices. Okay, and so that's something we get for free. And it also follows from this, the normal matrices are exactly the matrices which can be unitarily diagonalized. So there's a unitary change of basis, which brings them to diagonal matrix. So that's normal matrices. And I think there'll be very few times in this course where we're working with matrices that aren't normal. Certainly when our eigenvectors and eigenvectors come into play, the matrices will always be normal. Now, if your matrices, if you drop the sort of the star closed, life gets a lot more complicated. There is a theorem due to Schur that tells you that every square complex matrix is unitary similar to an upper triangular matrix. And again, there's a proof of that in my notes, although I'm happy just to use it. The point is that for a triangular matrix, the eigenvalues are the diagonal entries. Okay, so this, so you get so it's probably more useful to say it's unitarily similar to upper triangular matrix, and the eigenvalues of the matrix are the diagonal entries of the upper triangular matrix. And so I won't be worrying about this. Is a useful fact, and it may help solve some of the exercises. Okay. Any questions at this point? So I want to stop sharing just for a minute. The couple of things. So I'll do the administration now. It gives us a kind of a break, even if it's not very interesting. I have a web on the field web page. There's a link to a web page that I'm looking after. On that web page that I'm looking after, there are references to various notes or links to various notes, and also links to some talks from older courses that are somehow related to what we're doing. And there's also information about the assignments, and in general, I'll be posting anything I want spread on that web page. Now, the recordings of the lectures are on the field web page, and the slides will also be there, I think. I haven't actually talked to Shu Chen about that yet, but I don't think there'll be a problem. So the slides will be on the field web page, and the links to the lectures, the recordings will be there. Any questions about that? Okay, now on my webpage, well, actually, this is in both places, but there's more detail on my webpage about the system for the assignments. Basically, you have to write up solutions and submit them to me. I'll eventually, they'll probably get you to send them directly to Maria at the TA, but for the moment you send them to me. Now, please make sure that don't send me 2 messages with the same header, because I'm going to be throwing these things into a file, and if you give me 2 messages to the same header, I'll end up with one, like I end up with 1 file instead of 2. So don't send me 2 messages with the same header. If you're sending a set of solutions, it's very best if you just have if the header is just your name and which problems are being solved in that file. And if you want to ask any questions, just do something different. But so if you're sending don't mix up the solution to the assignments with questions about what's going on. Send that separately. Is that clear? I mean, the reasons are fairly obvious if you think about it. Okay. Now, as I said, the system is you write out the problems. We check through them. If they're correct, we record 5 marks. Otherwise, there's some processing involved, and you're looking at 4 marks. And so your goal should be to do something around 50 problems. And if you do that, then you'll get a good mark, which by my standards is, say, 90. Okay. If you want to do beyond that, then you've got to surprise me at a few points. Okay. There's also an option for doing a project, but we just discussed that separately. Again, any questions there? This is a system I've used for my graduate courses for forever, and I think for Zoom it seems to work better than that. Trying to run an exam. Okay. Now, what's the other thing? I talked about the assignments. Yeah, office hours. So I would like to have the office hour for this course right after this lecture. So at 3:30 on Mondays. If that doesn't work, then let me know. Okay. Now, someone's asking is when will the problem sets be due? What's going to happen is in a couple of weeks' time, I'm going to warn you that I'm going to close off the current list of assignment questions. So you'll get a list of assignment questions. That's called assignment 1. And so you can hand in. And so basically, the easy way to think about it is you have 4 weeks to do questions on that assignment. And then the next assignment, 4 weeks, and the next assignment, 4 weeks. Now, it's quite important. This is a bit different from the system we used to, and it doesn't reward procrastination. Okay, don't think that you can sit down last week and do a bunch of problems. There are some easy problems there, but they're not all easy, and you don't know which are easy and which is hard. And that's the point of the system, because in the real world, you dream up questions for research, and you don't know whether they're hard or not. And you have to make decisions so that I'm not worried. So the point is, there's easy questions, there's hard questions there, and you can't be sure on what order they are. Okay, and so there's more comments on the web page. So you can think. So your goal should be to do. We've got 12 lectures, something like the order of 4 or 5 problems a week. Okay. Now, if you have questions about the problem, I'd be very happy if you just ask them in class, because other people will probably have the same problem. Otherwise, you can send me an email. I'll have at least 1 office hour, and we can also set up Zoom sessions. Any questions? No. Okay. Mary? Oh, you're all happy.
Hello, Professor. I was just wondering, are we only graded on assignments? Do we not have
Yes.
a midterm or a final exam?
There will be no midterm and no final.
Okay. Okay. Thank you.
Okay. As I said, this is a system I've used for my graduate course in algebraic graph theory for a long time, and it works pretty well. Okay. And so the system is that you have, I don't mind which problems you do. And if I were you, I would pick the easiest ones first. And there will be some in there that are quite easy, and there'll be some in there that are longer. Although if you find yourself 4 pages into a solution, it may be a good idea to ask a question, because I don't really have the patience to grade really long solutions. Okay. And I said, and there's we will, if you do something a bit beyond what the problem actually asked for, then you'll get bonus marks. And I'm willing to be reasonably generous about that. But again, if you want to do extra work on the problem because it interests you, that's fine too. And we can work out something, just let me know. But don't do huge amounts of work and then dump it on me and say, I want this to count without clearing with me first. Okay, let's go. If there are no questions, we'll go back to the talk, to the lecture.
Excuse me, can I ask a
Yes.
question about what we just discussed?
Yes, definitely.
So when we introduce the norm that compare the distance between two matrices, is this because we want to prepare ourselves for the quantum walk algorithm?
It comes up at various points. It's so it's simply when we're trying to prove things about properties of quantum walks, we will be using norms at some point. Okay, so that it comes up. So, for example, if we have a quantum walk which we haven't defined, it tends to if it visits a certain state, tends to come after a certain time. It'll get very close to that state again. And to make that statement precise, I need to use norms. So if I say two things are close, what does that mean? Well, what it's going to mean is some norm that's small, or the norm of the difference is small. Does that make sense?
Yeah, and when we are discussing like the normal matrices, it is a subclass of the unitary matrices.
No,
or-
no. Unitary matrices are normal. There are normal matrices which aren't unitary. The all-ones matrix, for example.
Oh yeah, sorry. I was looking. Okay.
Yeah. I'm very glad to answer these questions. So you've got no idea. So I'm not sure if I'm trying to get back into my Zoom meeting now. It doesn't want me to. I have to restart. I didn't stop sharing. No, just stop sharing and then restart. And there we are. Yeah. So, are there any more questions? Oh, okay. Thanks for the ones I did get. Yeah, so I've talked about normal matrices, and as I said, this means unitary or Hermitian. If two normal matrices commute, their product is normal, but we don't need that. So the next class of matrices I talk about are projections, and I'm going to do this in a moderately formal fashion. So I'm assuming to talk about projections, I'm assuming I've got an inner product space. Okay, so that's going to be R to the n with the Euclidean inner product, or the C to the n with the usual inner product, or the space of n by n matrices. Okay, now the adjoint, if I have a linear map, that should be LV to V, and we can fix that. Then the adjoint is defined by the requirement that the inner product of U with LV is equal to inner product of L star U with V. Okay, so if you're using the ordinary real matrices and the ordinary inner product used to, then that star is just a transpose. And so it says when you move the operator across the inner product, you replace the L by an L transpose. And if it's symmetric, it doesn't change, of course, and that's why it's important to be symmetric. And in this case, since we're working more generally, we'll say if L is equal to L star, then L is self-adjoint. Okay, so self-adjoint would normally mean emission or symmetric unless we're working with a vector space of matrices. And so self-adjoint is safer. If you're dealing with infinite dimensional operators, then the terms self-adjoint and symmetric have different meanings, which we won't go into. Okay, so symmetric matrices and emission matrices are self-adjoint. Normal matrices are not necessarily self-adjoint. Okay, I mean, U star for a unity matrix is the inverse, which is not in general equal to U. And this is related to something I mentioned several times. If you have a linear map from a vector space to itself, and it fixes the subspace U of V, well, it fixes that subspace if and only if its adjoint fixes the orthogonal complement. Now, this is just an easy exercise from the definition, and I'm not even going to assign it. So it's completely straightforward. So now, having done that, we can define a projection as a linear map from a vector space to itself that's self-adjoint and idempotent as square is equal to itself. In a sense, the most general example we need is if U is a subspace of V and U under UD is an orthonormal basis for U, then this sum is a projection. Now, I've got to be careful here. So UI, think of it as a D by 1 matrix, and U star is a 1 by D matrix. So this is a D by D matrix. Now, for those of you who've done some physics, this, of course, is just this is often called an outer product. So this is a sum of outer products. Just those two words. And this is a projection, which you can verify. And its image is U, the subspace you started with, and its kernel is U perp. Now you can see that the kernel contains U perp because U star, something in U perp is going to be 0. The other comment I'll make is when in your linear algebra course you talked about using Gram-Schmidt, you compute projections onto subspaces. You realize, okay, you want to compute a projection onto subspace, the first thing you got to do is to find an orthogonal basis for the subspace. So you do that. And then you do some fiddling around and eventually compute the projection. But you might be given some sort of formula, but it's worth noting you can write that projection, you can write that operation as a matrix. And so when you apply that matrix to a vector in the big space, the result is this projection on the subspace. So this is something which in some sense hidden from you, that you can write the projection in this explicit form. Okay. And well, that will matter to us later, so that we can construct the projection from an orthogonal basis. That's the executive summary. Now, so a few general comments. If P is a projection, then so is I minus P. And in this case, let's just, I minus P squared equal to I minus 2P plus P squared, which is I minus P. So projections come in pairs. P is a projection onto U. I minus P is a projection onto U perp. And so P times I minus P is equal to 0. So projections onto disjoint subspaces have product 0. Now I've got to be this is completely confusing. If two projections P and Q have product 0, the term we use, and this is the rule, is that P and Q are orthogonal. So if two projections are orthogonal, we mean that their product is 0. Okay. Now this is completely confusing because we construct a projection for an orthogonal basis and orthogonal vectors, and it's not at all clear what the relation between the two terms usages are. But there's nothing I can do. I can apologize, but it's not my fault. So if two projections are orthogonal, we're just saying that their product is 0. And so P and I minus P are orthogonal projections. You can, if you think about it long enough, give us kind of a geometric description, but it's not worth the trouble. And there's a few facts about commuting projections, which I don't think I'll worry about. Now, so the point is that projections are nice matrices, and we often try and represent write our matrix, other matrices as linear combinations of projections, and so that's one reason we'll need them. They're also used in optimization problems to find you've got a vector, you want the vector in the subspace which is closest to the vector you have, and then you use projections there. We're not going to be using them in that way. Okay, so and so now we come to one of the most important tools that we'll be using in spectral decomposition. And so let me just go on. Now, so I'm going to assume that I've got a normal matrix, and for the moment I want to make distinct eigenvalues theta 1 through theta d. Now, I'm not assuming the eigenvalues of M are distinct, so M can be an n by n matrix, and it's got only d distinct eigenvalues. Okay, so some of these eigenvalues may have multiplicities greater than 1. Okay, so I've got eigenvalues, and to each eigenvalue there's an eigenspace, and to each eigenspace there's an operation of projection onto the eigenspace, and we will let E sub r be the matrix that represents orthogonal projection onto the theta r eigenspace. Okay, now then, because it's a it represents orthogonal projection, and projections p squared is equal to p is self-adjoint, we get that ER is equal to its conjugate transpose, and is also equal to ER squared. Okay, so it's emission and idempotent. If R is not equal to S, then ER and ES is equal to 0, because it's a projection on the intersection of the theta R eigenspace and the theta S eigenspace, and that's 0. And so these ER and ES in this case are orthogonal, and the sum of the projections is the identity, because we're assuming we get the eigenspaces. We can find an orthogonal basis for each eigenspace. The union of those orthogonal bases is an orthogonal basis for the entire space. And so from that, the last property holds. So if the matrix is normal, we get these projections. Now at this point, here the eigenvalues are playing no role. Okay, we're just dealing with eigenvectors. Since ER is a projection on a theta R eigenspace, if I want to, I could compute it by finding an orthonormal basis U1, say through UM for the eigenspace, and then taking the sum. Let's write this down. Sigma UI starred. So if I take an orthonormal basis for the eigenspace and now take this sum, that sum is the projection onto the eigenspace. So we can compute it. Your life is, actually should be a star. Your life is simpler if the eigenvalue is simple, because in that case, there's only one term in the sum, and you're looking at a vector of the form you starred, which is a rank 1 matrix. And so that makes it's very easy to write down, whereas if you've got a bunch of these things, it's a bit of a pain to add them all up. But so if the eigenvalue is simple, then the projection is easy to work with because it's a rank 1 matrix. But we have these properties. Okay, let's get back to the... So this is really just the diagonalization of normal matrices written out in a slightly different form. Okay, so this is the matrix form, the early descriptions in some sense the geometric form. And this is one thing that happens in linear algebra. There's usually often more than one way of just presenting a given result. You can describe it geometrically, you can describe it in terms of matrices, you can describe it in terms of linear operators. And part of the trick of working with linear algebra is learning to move backwards and forwards between these different descriptions. So continuing with those matrices, there's a couple of things. The trace of E sub r is the dimension of the theta r eigenspace, which sort of follows from, well, does follow from the stuff I was doing with the expression there. And the other point is, of course, each column of the R is an eigenvector for M. And so you get that M times E sub r is theta r times the R. Now, so it follows, if matrix M is equal to M times I, and I is equal to sum of the theta r's. There it is. So that's that. And then M theta r is equal to this. And so we get that M is equal to this. And again, the theta r's are the eigenvalues, and the ERs are the projections. We'll call them spectral idempotents. And so we've now expressed M as a linear combination of projections. And this is what I would call the spectral decomposition. But one reason spectral decomposition is useful is because if f is a function defined on the eigenvalues of m, then f of m is equal to sigma f of theta r e sub r. Now this is useful in very many ways, and I don't know if I'm going to put in a, I'll do it next. One consequence of this is that the if m has spectral decomposition sigma theta r, then m star has prediction theta r bar er. But I want to talk a bit more about this. This comes under the heading of what the analysts would call functional calculus. Let me give myself a page to work on. So we have m equals sigma. Let's look at m squared. Well, we do the obvious, but you're going to get a sum sigma theta r theta s. Yeah, yes, some double r and s, which is equal to the sum theta r squared. And so then by induction, you would say that m to the k is equal to the sum Now, sometimes this is advertised as the spectral decomposition gives you a nice way to compute powers of a matrix, but I've never had to actually use it to do that. It's still important. The next step, of course, if PT is a polynomial, then P of M is equal to sigma theta r. So we can write that, express any polynomial in our matrix in terms of the spectral decomposition. Okay. And we're going to use this eventually to express, to get, well, I can actually do it now. It's probably on that slide or something, but I'll do it now. The general statement is if f is defined theta 1 theta g, then we can say that f of m, well, I can take this to be a definition or a theorem depending on the details, but f of d then f of theta. So e.g. if the theta I are non-negative, then m to the 1/2 is equal to, oh, it's just playing up on me. Square root the exponential of m and so this gives me a formula for the exponential of a normal matrix. Now, it's reasonable to ask, how do I know this is actually equal to the sum sigma? And my attitude is that I'm not going to care. There's various ways you can verify it. This becomes more of a question when you're dealing with operators in exponential spaces, but in our case, well, actually, it's probably not too hard to work out the basically work out the stuff in sigma. Let's do it theta to the r. Okay. To replace m to the k by this, and then you've got a double sum, and then do the obvious tidying up, and wave your hands and say everything converges when I need it. and deduce these two things are equal. Now, most of the time, it doesn't really matter. It's simply if you've got some function defined on the eigenvalues of your matrix, then you can compute the value. You can function f, and then you can compute f of m. Okay, and it will mean what you think it means. So this is what example of what is called the functional calculus, and this is why we need the spectral decomposition as much as anything. As I said, you can use it to define powers of matrix, but as I said, I've never had to do that in practice. But I've done this sort of thing, these sorts of things all the time. So it's quite important. The other thing that's important to realize is that the spectral idempotents of a normal matrix A, the polynomials in A, you can basically assume that any matrix I mention from now on is normal. If it's not, I'll warn you. Okay, so the spectral idempotents of A are polynomials in A. Let's make this a real word. The trick is to find these. I want to prove that E sub R is a polynomial in A. Okay, so the obvious way to do it is to write down the polynomial. There might be other ways of doing it, but I would write down the polynomial. So what's the polynomial I'm going to use? I'm going to use this polynomial, which is t minus theta j over theta I minus theta j over all j not equal to I. So that's a polynomial of degree, if there are d eigenvalues, it's a degree d minus 1. And if you check, then Li of theta j is equal to the Kronecker delta I comma j. So it's 1 if j is equal to I and 0 otherwise. And so now using I say bispectral decomposition, technically I'm using functional calculus, you get that del sub I of A is I. A is equal to E sub I. Now, I tend to combine, so there's two parts to the spectral decomposition sense. The first is we have this formula saying A can be written as a linear combination of these projections. And then there's the second part which says you can compute f of A from that. And sometimes people distinguish between the two parts. I think of the two things as being spectral decomposition. If you're an analyst working with infinite operators, you may want to break up, but we're not. Okay, so this says that, and so this is our proof. Now, this is a useful fact, and it's not as well known as it ought to be. So the spectral idempotents, I wrote down a number of properties. One important property is each idempotent is a polynomial in the incoming matrix. So if a matrix is unitary with spectral decomposition, then you can prove that for a unitary matrix, the eigenvalues are complex numbers norm 1. That's a little exercise. And so in that case, that means the spectral decomposition looks like this, where the theta r are real. So this, as theta r runs over the real numbers, this runs over the unit circle. And so if you define H to be this sum, then you get U is the exponential of IH. So this proves that every unitary matrix is an exponential of I times H, where H is emission. Now, a few comments. IH is skew emission. The complex conjugate of IH is minus IH. But I itself, okay, now, but this is a very important theorem. So it's saying that, you can do it. Every unitary matrix is an exponential. So this is one reason why the exponential matrices are so important in quantum physics, because your operations in quantum physics, well, they're either measurements or they're applying unitaries, and unitaries are all those exponentials. And in this context, H will often be called the Hamiltonian. Now, if you've had a course in classical mechanics, this has some meaning, but if you're like me and haven't, then maybe it doesn't. But it is called the Hamiltonian. So every unity can be written as a form of x equals I times H. And in that case, the physicist would be referring to H as the Hamiltonian for the system. But we're getting that every unity matrix is an exponential. And the comment here is that if you take something slightly more general, you take X with ITH, where H is emission, then, and you get the family of matrices U of T, then that family of matrices determine a continuous quantum walk. Now, I'm not going to define quantum walks or go into their properties now, but the point is, well, I have defined it. And so studying quantum walks, continuous quantum walks, is exactly studying this family of operators for a particular matrix H. Now, in our case, H will usually come from a graph in some form or another. It might be the adjacency matrix or it might not be, but there will be an associated graph. And so a quantum walk is just a unitary. And so this is why I started by saying that these things are very important. And in physics, as I said, they're using unitaries all the time, and every unitary is an exponential of I times H. Over time. I've gone far too long. Okay, I'll stop. I've got some examples and notes. I'm sorry for that. I should set an alarm. Okay, that's it for this week.